Alright, well, welcome to Lecture 1 on General Relativity. This lecture will be very short. Basically, I just want to kind of give a quick rundown of what I'm planning to cover in this course, give or take. Loosely based on, sometimes not so loosely, but sometimes loosely, based on Space-Time and Geometry by Sean Carroll. This is a really nice book. I used to have a really nice version of it, and then I lost it, and then so I have the cheap version. Some other books I might look at on occasion, of course. Here's another one, Gravitation and Cosmology by Steven Weinberg. This book is that's a book. That is kind of the counterpoint in some sense to this book here, which is Gravitation by Misner, Thorne, and Wheeler, MTW. This book, I think maybe I first learned some relativity out of this book. I did a ton of homework in this book. Lots of nice index juggling problems in this book. Maybe I'll give you some of those to work on. I don't know. But this book takes, it would say, a geometric viewpoint. It's very big on trying to write equations, quote-unquote, geometrically. In other words, coordinate-free. It's all about coordinate-free. And in contrast, Weinberg's book is like, coordinate-free is nonsense, everything should be done in coordinates, and here's how you do it in blinding detail. So, you know, each of those books has their place. And then there's another book which I have spent some time looking at, which is General Relativity by Wald. This one is of a slightly later era. I think Weinberg and Gravitation are both from the 70s. I think this one was like from, I'm trying to remember when this one was written. 84. So, but it's a good book. Now, I don't remember math-wise how Weinberg's book is. Weinberg's writing style is unique, but this one is very well written. I think from what I remember, the mathematics in Wald is pretty good. The mathematics in Gravitation is, yeah. It has some problems, but it's, you know, it has so much content, it's just ridiculous. And the mathematics is easy enough to fix, I suppose. But in contrast, the mathematical clarity of Carroll's book, I think, is considerably more. It's a much more modern book. I'm trying to remember when this thing was, but he had these things out in notes that were available for free, in part for a while. 2013, I guess. Yeah. Anyway, I have a bunch of other books that we'll look at on occasion. Here's one I just got today. Geometry and Isometries from Special to Special Geometry from Isometries to Special Relativity by Nam Hoon Lee. This is this is interesting. It really does investigate the connection between hyperbolic geometry and special relativity, which some of the students of this course might be interested in. Should be careful not to break my table. All right, so let's give a quick rundown here of the topics in this course as I see them at the moment. All right, and listen, I'm going to try not to let perfect be the enemy of good, but I'm already falling short on that because I should have made this video like 2 weeks ago, and I've been writing and I should have just made the video. So anyway, already my overview is a little bit wrong. But anyway, so we start with special relativity and Minkowski space. What's Minkowski space? Essentially, it's four-dimensional R4 paired with a Minkowski metric, which is defined by that formula there. This is the repeated index notation. We'll talk more about that, all right? We need to talk about tensor calculations, the musical morphisms. I'm not so explicit on the musical morphisms. I'm just going to kind of raise and lower indices in here. If you want the explicit musical morphisms song and dance, it's actually quite clear in MTW. But, which is kind of funny, like MTW might be missing some of the curved space math, but the linear algebra, there's a lot of linear algebra, a lot of it in MTW. It's certainly one of the better places to look at, like, how do differential forms interact with each other algebraically, how to visualize them maybe, things like that. Anyway, then we'll move on to energy, momentum, four vectors, and physics. All right. And then I should talk about the Lagrangian formalism in classical field theory. Now there, because my intended audience includes math majors who never had a junior level course in advanced classical mechanics or whatever, I need to take maybe some time there to develop, what is the Lagrangian and how does that allow us to formulate regular mechanics, and then from that you get to what's called classical field theory, which is sort of classical mechanics of continuous fields. And general relativity would fall in that category. At least it can be described in that way. And then we'll talk about manifolds. Manifolds, curved space on which you can do calculus. Basically, that's it. As I said, calculus on curved space. That's Carroll's chapter 2. Enter the metric. So this is the metric. And now I say the metric, but to be clear, in analysis or standard mathematical literature, a metric essentially means it's a particular tensor on a manifold, which is type 2-0, I think, or type 0-2, depending on which book you look at. But anyway, say type 2-0, and at each point it gives you an inner product, which is a symmetric positive definite bilinear form of the tangent space. And so technically speaking, the metric we look at in general relativity is not one of those. It's not a Riemannian metric. It's instead what's known as a semi-Riemannian metric, which makes the mathematics considerably more annoying. But there are extensions of the results that you are maybe already familiar with from linear algebra to the context of semi-Riemannian geometry. So it's not all is not lost. It's a little bit more technical. But this difficulty is unavoidable because it's already with us at Minkowski space, where we have to look at special relativity, which basically is, of course, based on this Minkowski metric, which again is not technically a metric in the strict Riemannian metric sense of the term. It's a semi-Riemannian metric. It has there are things called null vectors. All right, it's symmetric, it's non-degenerate, but it's not positive definite because there exist vectors whose Minkowski product is 0, and yet with themselves is 0, and yet the vector is not 0, so-called null vectors. Excuse me. Those correspond to light rays. All right. Anyway, then on to chapter 3, curvature. So chapter 3 of Carroll describes curvature. If you took a course in elementary differential geometry, you've already seen the two-dimensional version of this guy, the Gaussian curvature. But this is four-dimensional curvature, and so we have to develop something called the Riemann tensor, the Riemann curvature tensor. It's a rank 4 tensor, 4 indices. And then there's a contraction of that known as the Ricci tensor, I believe. And then there's a contraction of that further, which is called the Ricci scalar. Probably the Ricci scalar is kind of sort of the Gaussian curvature we looked at. If I remember right, Gaussian curvature is a scalar, right? It's the coefficient of like the top form in the calculus on the surface, something like. Anyway, I'm a little rusty. Let me not bloviate about that. Anyway, curvature in 4 dimensions. We'll look at how that allows you to talk about the covariant derivative. Covariant derivative is a way to take the derivative of objects, tensors, differential forms and such, on a curved space in such a way that the derivative of the object is again an object of the same type. So if you just take the partial derivative of a tensor, you don't get back a tensor again, you get something else, generally speaking. If you take the covariant derivative of a tensor, you get a tensor. So that's a useful concept, covariant derivative. That does tie into also the topic of parallel transport. How do you move vectors around on a curved space in a logical, consistent way? Geodesics. These are the paths of minimal distance between points, also very important, like great circles on a sphere. Physically speaking, these actually are very interesting later. And then and then here's the equation. So if you want to find the geodesic, you got to solve this here differential equation. These gamma, mu, rho, sigmas, these are called the Christoffel symbols. They're defined in terms of particular derivatives of the metric. So if you know the metric, you can derive the Christoffel symbols. If I recall correctly, they're based on second derivatives of the metric, I want to say. I'm not, they may be first derivatives of the metric. Goodness gracious, it's been a while. It's been a minute. I've had 2 courses in relativity before. I had a wonderful course from Dr. Arkady Kafetz of NCSU. He worked on, a lot of his life's work was on quantum gravity, and he a student of Wheeler, actually, of Misner, Thorne, and Wheeler. Brilliant man. Wonderful course. I will at times refer to his course. And then I also had the pleasure of taking, that as an undergraduate, I took that course. And then as a graduate student in physics, I took a course in general relativity from Martin Roczek of Stony Brook. Again, a masterful course. Really, really beautiful. His way of doing things was in terms of the tetrad formalism, which I'm not sure, I haven't studied Carroll's book enough to know if that's really in there or not. I would like to touch on that because I think it's interesting mathematics. And I don't think that's as widely known, but it's a more elegant and beautiful way of formulating the theory, the tetrad formalism. It works on this the Vielbein, this 4. It's essentially a frame calculus that supports something called the spin connection, and that naturally leads to writing equations of supergravity in really really nice way. And so that's not surprising. Dr. Roczek is one of the early pioneers in supergravity. He wrote the book on it and things like that. So I was very blessed and privileged to take a course with Roczek, and I'll talk about that from time to time. Let's see here. So I forget which book we used for Roczek's course. I don't remember. Oh, it was oh goodness, I want to say either Lawson or Lawden. At some point I'll get to that book. That book is good for the discussion of, what I'm about to talk about here. So then once we get curvature settled and talk about our geodesic equation, all that jazz, then that allows us to define define the, oh goodness, it didn't even make the list, but to define the Einstein tensor, which I think is essentially here. Sometimes this combination of the Ricci tensor and the Ricci scalar and the metric, like such, is known, if I remember right, that's the Einstein tensor. So the Einstein tensor, which is a rank 2 tensor, equal to 8 pi g. This is that, the gravitational constant like you saw in Newton's universal law of gravitation. That's the big G. Don't ask me the value right now. I haven't taught physics in a little bit, so sadly I forgot the number. Okay, but anyway, and then this T mu nu is it's a lot of things. This is the stress energy tensor, so this includes pressure, energy, shears, and strains. So you can describe basically the quirks and features of your favorite ideal gas or dust or whatever. In short, what this equation says is, and this is really the whole course, it says that the geometry of space and time, which is the left-hand side, is equal to the presence of mass energy, that's the right-hand side, coupled by g. And this g here is very, very tiny, which means gravity, in some sense, is weak, certainly compared to the other fundamental forces. But this is it. This is Einstein's field equations. Our goal in this course is really to understand this equation, to formulate it, and perhaps to understand other methods of formulating it besides just the way that's in Carroll. Let's see here. So we'll talk about Einstein's field equations, their properties, the equivalence principle, and also a little bit about alternate theories. Now, I should mention, you could say a lot of things about physical motivations of relativity, physical consistency of relativity. This course will not have much to say in those directions. I will be focused. I will make definitions and really try to focus more on mathematical formalism than physical plausibility. Physical plausibility is dealt with in great depth in Carroll, and I want you to read it. And I'll say a little bit about that here and there, and certainly, for example, Dr. Kafitz's course. I was looking back through my notes, and I mean, I think easily 50% of our course was based on explaining the physical plausibility of certain constructions and so forth. And so I'm not saying that's not important. Certainly it's important, but it's just not where I'm going to take this course. Then once we have the equations of gravity settled, we'll talk about the Schwarzschild solution, properties, singularity, black holes. So the Schwarzschild solution was one of the first non-trivial solutions to Einstein's fields equations that was found around World War I. It's elegant, beautiful, and has had tremendous application in black holes, black holes have in my lifetime gone from being like a theoretical possibility to being the dominant part of the story in the large-scale structure of galaxies. Like not a given galaxy, how it rotates, the stars rotate around the galactic center. We think there's like a supermassive black hole there and stuff like that. Because you can see like, solar systems whipping around something really, really fast, and that something has to be stupidly massive to gravitationally bind things moving that fast in those kind of tight circles. Anyway, so maybe we're closer to understanding the dynamics of galaxies and gravitationally, because we know about black holes and the kind of insane mass that they can have. But certainly not everything is understood. I haven't really said anything about it, but at least at the end of Carroll, he talks about the fact that, there's just a standing inconsistency between how we formulate quantum mechanics and how we formulate relativity. They're at odds, and the way that they're at odds, it's not really super far into either of their formulations. It's kind of at the start of things. There's just like this fundamental difference of opinion on how you should look at the world, and yet gravity describes gravity pretty well, and quantum mechanics has been pretty successful in explaining everything from solid state electronics to tons of chemistry, there's so much quantum mechanics is explained in the world, and yet we also have experimental tests of general relativity. So how do you reconcile those things? Physicists want to come up with a consistent and unified theory of nature, and we don't like it when you have two theories which are at their base, irreconcilable. So that's, one of the things I respect about physics is that when there's a logical inconsistency in their basic theories, they own up to it, and they recognize it, and they say, we've got work to do. As opposed to some other fields of study where I've been in introductory classes and been exposed to 6 or 7 contradictory theories, and never so much as an apology for their contradiction amongst each other. Anyway. And still those people say they're scientists, but whatever. I move on here. So, Schwarzschild solution, then we talk about gravitational radiation. I skipped chapter 6 because that's like hard black hole stuff, which I probably won't have time for. And then gravitational radiation. So there, what you do is you look at what's called linearized gravity, which is easier to solve, and in that linearized gravity you can solve and find solutions which represent gravitational waves, and you can kind of, without too much effort, derive some basic properties of gravitational waves and things like that. Also interestingly, when I was taking my last course in relativity in school, we had not discovered gravitational waves. We had not observed them. We were talking about it. It was a distant possibility. But I think about 10 years ago now, we actually observed a gravitational wave using one of these super massive laser arrays, which can basically detect, minute deviations from in the curvature of space-time over large areas. Anyway, I think it was LIGO that discovered. again, I forget the details there. Who discovered the gravitational waves? Um, but I was kind of surprised when I heard about it because they were talking about setting up um, an experiment which was like as big as the Earth-Moon system or something, like a triple of satellites that were like really, really, I mean, relative to the Earth and Moon, they were that big, that kind of scale, to set up like a huge triangle with lasers to detect the waves, and then the Earth-based one, I believe, um, actually detected it. So it was kind of, oh, cool. Anyway, they have been detected. Not a lot of them. It takes really, really um, incredibly destructive events to create gravitational waves that you can measure. Things like, oh, I don't know, like a neutron star, um, like getting absorbed into a black hole or something like that. I don't know. It takes big cosmic events to make gravitational waves you can measure very far away. And if you were close enough to feel them, it probably wouldn't be good for you. Um, because for the most part, gravity as we experience it doesn't have dynamics. It's static. It is what it is. Um, like we don't feel the sun moving as we're going around the solar system, right? It's not like we feel, oh, the sun is pulling on us, and then it's pulling on us like a little bit less, right? Like the sun is just pulling apparently a constant rate, and like the same for the Earth, right? The way we're gravitated, it's not varying with time so much. It's static. So like the dynamics of relativity were certainly hidden until the past century. Um, and then I'll talk a little bit about cosmology, the maximally symmetric universes, the Robertson-Walker metrics, perhaps a little bit about dark matter, the cosmological constant, and also inflation. Interestingly, before I took relativity, the cosmological constant was kind of poo-pooed and thought it to be possibly a mistake of Einstein. And then we made more experiments, and people realized, oh, we kind of need that cosmological constant in there in order to fit the data that we're seeing in our astronomical observations. At least that's where the story was, as I recall it a few years ago. It's physics. There's no telling where experiment has taken things since I blinked my eyes. Um, and then inflation. Inflation is a very interesting subject. We'll talk some about that. Um, so that's kind of the course in a nutshell. The book I was mentioning for this stuff, maximally symmetric universes. I think we used Lawson. I think it was Lawson. That was the book that we used in Rochek's course. It's a nice book. I think it's out of print. I just have like a photocopy of it. Hey, maybe Dover's got it by now. I don't know. But okay. So anyway, I'm still, and then I haven't shown you these, but Dynamics and Relativity by McComb. Schutz is like a mathematical physics handbook kind of thing. Resnick, Rindler. These are good special relativity books. So I'm also trying to come up with homework for the course as we go here. I have some ideas, but I haven't written your homework yet. My apologies. Anyway, that's it. I was going to make this short, but apparently I can talk. So, sorry guys.